So welcome everyone to this workshop. Thank you very much for joining us. If you haven't already, check out our Discord server where you can ask questions that will last a bit longer than this Zoom call, although you're also welcome to use this chat here. During the workshop, please keep your microphones muted unless you're directly asking questions for obvious reasons. Same goes for cameras. It just makes it easier to keep track of the speaker. Apart from that, I'll pass over to the speakers and hope you all enjoy the workshop. If you just take over screen share, Ilya. I think that should work.
We can start then.
There we go.
So, hello everyone. I think it's high time we started this. I don't really have sound. I'm just hearing something coming from the room, so I just assume that we can start. So thank you for coming. My name is Ilya, and today I'm going to be talking about building CI/CD pipelines in the world. We're going to see how we can test our firmware on the real devices and how we can introduce some kind of security testing, static and dynamic. I'm presenting today as a part of the TechMaker community. A couple of guys gave a talk yesterday about the CAN bus sniffers. So we kind of collected our experience, me working for my company and their experience. And we'll start to, and we'll do some kind of, combined presentation. You shouldn't probably treat this as a cut and dry list of recipes that will 100% work for you, because my experience mostly was with IoT devices, and the guys, other guys from TechMaker, they mostly work with cars. So it's gonna be more like, mindset, experience sharing, some advices. A lot of those things will be applicable to a lot of areas, online, offline, like maybe you develop, nuclear reactors or something, still gonna be applicable to you. So yeah, let's start. This presentation was inspired by a question I've heard a couple of times, especially when people learn that I do this thing or did this thing for a living in the past. And the question was, is it even possible? And my first reaction was like, duh, of course it's possible. But then, I remembered myself like 3 years ago, just starting with this thing, having no idea what to do, what is possible. So now I treat this question in kind of different way. Is it even possible in a meaningful way? Is it even possible to generate some value? Or are we just doing this, to put some mark on a checklist that we kind of test on the real hardware? And the answer hasn't changed. It's duh, of course it's possible. But for this answer to be, some kind of advice, the advice and the theme that I'm going to be returning to in different parts of this talk is just start small. Start small, start somewhere, anywhere, basically, and sometimes even start silly. We've done a lot of silly things that in the end worked for us really well, and we kind of kept rolling with them. So with this kind of approach, I would like to design a simple CI/CD pipeline as a person who to do this. You probably have some elements of this pipeline already, like, you have a step that checks out your sources from your source control system. The sources are built somewhere, and then you store that artifact in some kind of a cold storage, or you publish it onto your backend. That will depend on your distribution model. If you don't have those, my condolences, go do that first and then return back to this presentation, something like that. Also, you may have some kind of unit test during your build process already, especially if you design your firmware in a platform-independent way. That's kind of easier to just test your firmware for embedded devices on x86. And you may have also some kind of security testing, maybe in between the checkout and the build, or in parallel to the build. So some of these elements might be present. But the most problem people might have, in my opinion, is with steps 3 and 4. How we deploy on real hardware, and how then we test these things on real hardware, and what should we be testing. So in case with IoT devices, you probably kind of can cheat here and do some kind of end-to-end testing, just deploying via the over-the-air update and start testing it like that. But if you do that, you run into the problem that this approach is very limited. It's really fragile too, so you outgrow it really, really fast. So today I'm gonna be talking about how to get a bit closer to the metal, start connecting some other things to the hardware that will help us testing. And then we'll see how this pipeline evolves or can be evolved into something not so, simplistic with a lot of possibilities. So this kind of talk separated a bit into several parts. I'll talk about hardware first, all the harness you might need to really extend your testing horizon. Then we'll talk a bit about software that's going to be running and helping us to make some decisions about our pipeline designs. And after that, we'll talk a bit about security testing too, and we'll run a small demo. So when it comes to hardware, if you read the synopsis for this talk, you probably know what we in my company built our testing infrastructure on, and that's Raspberry Pi. So this was kind of both a smart choice 3 years ago and to some extent even lucky choice, because we didn't understand what kind of possibilities Raspberry Pi will give us in the future, but we still ran with it. So we chose it because it was supposed to be our CI node, one of many CI nodes. So our first CI/CD node actually was a broken MacBook 12, but that's kind of thing in the past. So we chose it because it's a general purpose computer. A lot of CI/CD software has agents that are able to run even on ARM. So you can connect it to a lot of CI/CD software like Jenkins, GitLab, AWS Code Build, et cetera, et cetera. And another part why we chose it was because it has a Wi-Fi and BLE on board. And our end idea was to replace the mobile phone, because we had a mobile app that works together with our device. So we wanted to replace a mobile phone with a Raspberry. So in case of Wi-Fi, we're using it as both a router for our devices to connect them to the internet. And also if you have, some all over your device, like you maybe know that some drones are controlled over Wi-Fi, or have some kind of provisioning process over Wi-Fi. Raspberry Pi can also be your client in this case. And the same thing with the BLE. A lot of things are going with BLE provisioning, initial setup. And if you do some kind of communication, beacons or anything else, it can be a part of your communication infrastructure, some kind of service. So this $30 computer allows us to replace a mobile phone, be a Wi-Fi router, and our CI node. The other good thing about it is it has a 40-pin header. Some of those pins are general purpose input-output, so we can control other hardware harness that we connect to it. It also features a serial connection interface, so a lot of embedded devices have this capability to, to connect to them via serial interface. So if you're running on a budget and don't have an adapter, Raspberry Pi has this capability. Also, for USB ports is just godsend for us. We went with a conventional Pi instead of the Raspberry Pi Zero, because Y0 has GPIO outputs, you can solder them on top of it. With USB, it's a whole nother different story. And USB, we connect a lot of things to USB, and both USB and some pins on the header can be used as power sources for our devices. So some of our devices can be powered easily from 5 volts and up to 500 milliamps. So we use USB on the Raspberry for those. And some other things can be powered from 5 volt and 3.3 volt pins on the Raspberry itself. When it comes to downsides or other kind of inconveniences and peculiarities of Raspberry Pi, the only thing that really grinded our gears was that it's really sensitive to its power source. So official documentation states that for Raspberry Pi Model 3B Plus, you need to have 2.5 amps. And for the newer 4B, it's like a whopping 3 amps. And because of that, 3 amps on 4B, we just didn't even try it because we knew it won't be enough. Because when you start connect things to Raspberry, they kind of dip into the pool of current it has. And because we're running them, as I'll show you in the future, from USB power bricks, we don't reach the whole 2.5 amps. So after some napkin calculations of all the devices we connect to it, we've arrived at this magical number of 1.5 amps for the Raspberry only, because if you give lower current than that, it can kind of brown out, just hard shutdown when it starts to be loaded. And you don't really want to have that if it's your CI/CD node, you know. Also, we run some radiators, very cheap, like aluminum and copper radiators, because Raspberry is sensitive to heat also. All right, like I said, we use serial connection UART for communicating with a lot of our devices. And we found out that the pins on the header is kind of unstable. Maybe it was a power problem. But when we switched USB to UART adapters, that problem disappeared altogether. So if you want some reliability, I suggest you use this approach if you go with the Raspberry. Common chips that are used, that we used and tested extensively, like famous FTDI 232, has a lot of knockoff boards built on top of this chip. Works out of the box on Linux and macOS. macOS is kind of convenient because we did a lot of local debugging, so connecting these adapters directly to the laptop to figure out how do we even automate this thing, and then like switching back to the Raspberry. When we ran out of those, we kind of shorted the market, the local market for these adapters and the Raspberries and a lot of other things. When we started to buy them wholesale to scale, we tested one other chip that I can vouch for, Prolific PL2303. That one is more convenient because it has a built-in USB-A connector instead of, you know, running this mini USB cable that you might have hard time to find. And it works on Linux too, so Raspberry understands it no problem. On macOS, not so much. There are drivers for it, but those drivers are, I believe, unsigned and downloaded over plain HTTP from some Chinese site, so I don't recommend doing those and running with those adapters like from your laptop. And everything else you can find, you know, a lot of things need to be experimented with. There are some caveats with running USB to UART adapters. I don't know if you guys can see the right part of the adapter because mine is overlaid with Zoom, but there is a small logic jumper there near the pins that switches between 3.3 and 5 volt logic for UART. Sometimes you need to pay attention to that. If nothing's working, see if you're running this adapter in sync with your UART voltage logic. And sometimes, like, don't believe everything that's written on the device. We received one batch of devices with wires sorted to every pin we needed to connect to. We connected them as usual per labels. And then after half a day of pulling our hair out, we discovered that the wires for RX and TX were mislabeled and just wasted half a day. So right after that, we quickly test those things by switching wires to see if things work. And these small things, they sometimes even can be soul crushing, but I guess when you're in this business, you need to account for those things too. The other cool, smart, and really lucky idea too was using controllable relay modules. So we encountered the situation after running some simple tests that we really need to press physical buttons on the device, flip physical switches, and do this in an automated manner. And we thought between the relay modules and just running simple transistors for those. But in the end, we went with the relay module, and later we used them for power delivery control too. So conceptually, the relay is simple. There are pins in the back. One of those is ground. One of those is voltage that controls the relay. And then you have a pin per relay section that you connect to the GPIO header on the Raspberry, and you output 1 or 0 there, and just relay clicks into corresponding positions. And on the front, there are sockets. You put one wire, you solder the button, which is basically the key that locks or unlocks the circuit. You put one wire into one socket, and you put another one in another that has the desired default state for you. So we run buttons unlocked by default and power locked by default. This kind of power control, we started using it for power cycling tests. So some test stands just run like 10,000 power cycles and see if device survives that. It's a good test to measure the reliability of your device to this kind of voltage spikes. The other thing is, let's say you're running a critical process on your device, some kind of an OTA update or whatever, and you just test whether the device survives the power cycle somewhere in the middle of those tests. Let's say you start writing on the flash and then power cycle back and see if device boots. And one other kind of cute side effect of that, we are now running several labs, like the whole rooms. Some of those labs are really like a couple kilometers from our office, and it's the current year, so we are not even in our office, we're sitting at home. If the device hangs, instead of like going there physically and checking out what happened, just log into the Raspberry remotely and do a power cycle and see if it comes back alive. If it doesn't, well, you're kind of out of luck. Again, couple of caveats with these things. So for the power consumption, kind of current consumption that need to be taken into account is 50 to 100 milliamp per engaged section. So on the photo, we have three things connected. I would expect it would rob the Raspberry Pi like of 200 milliamps or something. So this needed to be taken into account if you power them from the Raspberry itself. Another thing, while this rated for 10 amps and up to 250 volts AC, and we ran at 230 and 110 volts AC devices through this, sometimes they came faulty, and this is just because of the bad soldering job inside. And you can kind of spot those relays because they start to hang sometimes, and you need to just tap lightly on top of them or just like flick your fingers nearby and then they switch. Those kind of relays, because of the bad soldering, they may not have the same, upper ceiling for voltage and current. But I would expect that up to like 4 or 5 amps is okay to put through this device. If you work with something more powerful, I think you know better than me what to use there. But these things they're kind of cheap. You can buy them by kilogram or whatever. And they're really easier to either replace the whole module or just take a Sharpie and cross out the section that is faulty. And the last thing we use extensively, USB cables, snaky boys. So we connect and power everything with them. Our devices that are powered over USB, our Raspberries powered over USB, some kind of adapters and stuff like that. You can control your USB powered devices through the relay with these cables. Just remove the isolation, cut the red wire inside, route it through the relay, and you have the same type of control that you might have, for wall socket power devices through the relay. Your biggest mistake with working with USB cables is really treating power-only cables that don't have data lines as like data cables that you want to route your serial connection through, for example. And sometimes they don't even come as marked as power-only or available or with a data wire. So kind of need to experiment. And we experimented with a lot of cables and found out that some branded cables did a really poor job, while some no-name cables did really well. And some of those were really good for power delivery. Some of those were really good for data. So when it comes to USB cables, good luck. I'm not even touching USB Type-C cable that is on the photo. By the way, it doesn't have proper markings on them. So cool trick for inserting the USB cable right from the first try is that usually USB logo is on the top of the connector and the manufacturer logo is on the bottom of the connector. But for Bang & Olufsen and say 20 other vendors, it's not right. So good luck, guys. And well, as one small company from California likes to say one more thing, there are really a lot of things that you can connect to the Raspberry. So on the top of my head, JTAG programmers are really popular, especially when you're working with some kind of digital signal processing, SOCs and microcontrollers, image boards. A lot of networking chips has JTAG as a primary communication interface. So you have USB to connect the JTAG programmer to the Raspberry. It works. When it comes to scaling these things, though, JTAG programmers can get really expensive, especially when you're vendor locked. But it doesn't mean that hypothetically there isn't some kind of cheap knockoff that is compatible with the vendor software that you can source like 2 boxes of those from your local bazaar the same day. But I mean, the possibility is non-zero. I'm not saying that happened ever, but yeah, those things kind of happen sometimes. SDR board, software-defined radio. You might want to use those if you test wireless protocols, especially custom wireless protocols that you develop. It's kind of good if you can get away with something cheap like a RTL SDR for $30, really good for scaling. But if you can't, if you need something like Blade RF, Atos, Pluto SDR, you can kind of build specialized stands for that. And sometimes even scale it a bit like to like 5 SDR equipped boards. But with high frequency signals, especially we're going into the Wi-Fi range and above, Raspberry Pi computational power is kind of not enough for that. So you can offload the kind of job to a desktop computer or a laptop and then SSH from the Raspberry into that computer and run that SDR computation. We used SDRs at my work to fake GPS coordinates. Kind of successfully. That's not actually entirely illegal, but there are some caveats with that. So you cannot, without a proper license, you cannot stream those coordinates to the medium where other people's devices can hear that and act on that. So make sure you're in some kind of isolated space when you do that. Analog to digital converters and cheap light sensors is pretty much everything you need to run cheap tests with anything that involves light. So say you're developing smart light bulb, or you need to check whether your indicator on your device is lit when you do some action to it. And really, we tried cheap and expensive light sensors too. Both of those were noisy enough to be a bit unreliable, but then again, not noisy enough so that we cannot calibrate them. And ADCs, they're also 8-bit, 10-bit, 12-bit, doesn't really matter. With that kind of setup, sorted together an ADC connected to the Raspberry GPIO header, you can even run tests that measure some brightness levels. If you have a device that changes brightness levels somehow, just calibrate those levels to different ADC readings or other ranges, and you can do that. Developing on top of that idea, this is kind of a setup we almost put in the production. RPR has a 2-megapixel compatible camera that you can connect to it. So when you have some kind of display on your device, or maybe even a light indicator that can change colors, you can put those things as some kind of box, isolated somewhere, and run either a photo or video stream over that camera. If it's a video stream, put it through FFmpeg, and then those images can be run through some kind of OpenCV recognition or even simple neural network. I know this sounds crazy, but training neural network today, especially for image recognition, takes a couple of hours from not knowing anything about that to neural networks that can give you 98% plus correct results. So those things are also available, just limited with your imagination. And other specialized things like power monitors, controllable power supplies, oscilloscopes, those things today, especially modern ones, they have USB connectivity, and they also have libraries for programming languages, different programming languages that can connect to those and control them, read data from them, and interact with them in all kinds of ways. So again, this is limited just by the specialization of your setups, what you need to run. We ran power monitors with ours to measure power consumption with good success. And every other little thing that you need to run this kind of setups, auxiliary things, SD cards, I'm not really endorsed by any of the manufacturer, but we had the most success with Samsung Evo SD cards. We have this running joke that SanDisk should be thrown away without even opening it. But SanDisk has an extreme line, which is kind of good. I mean, if you don't trust me, go to YouTube, see what people put in their Nintendo Switches or anything like that. Those things, however expensive, however reliable, they will die in several months because it's our kind of workloads, at least, write a lot of things on those SD cards, and they're not really suitable for, as a backup devices or for long life in general. Ethernet hubs and switches, we connect Raspberry Pi via Ethernet, so we free the Wi-Fi adapter to do our things. Some of those hubs, even dumb hubs, have power over Ethernet if you need those. It's kind of cool all-in-one package. And right now, when we run several rooms and, situate our device on real server racks right now, we use just 48-port server switches and stuff like that. USB power bricks, a really cool thing to save you even physical space, because when you start to really find a way to power a Raspberry, you can go with wall sockets, you can go with chargers like mobile phone chargers, anything like that, but you quickly run out of the socket space. And even if you have enough sockets, they kind of occupy a lot of space. So we run them with USB power bricks, 5-in-1, 60 watts. So this 12 watts per port, 2.1 amps per port, basically. And that is enough to run 3B Plus without it shutting down on the load with everything connected to it. Here we run the cheapest things available, our local manufacturer. You don't need to go anything luxury. As long as it provides enough current, it's good. Uninterruptible power supplies, definitely not a requirement when you're just starting. But when you unlock the ability to run some tests that take a day to even a week, you don't want some random blackout to interrupt that testing process. And blackouts sometimes happen. So you kind of need to think about those if you start to scale. Same with air conditioning. When you pack like 50 Raspberries and 50 devices in one room, they start to generate heat. You don't really need an industrial HVAC to cool those, like simple air conditioning units that people put in their homes will do. But this is also definitely a thing to think about. And then lastly, low interference space. You want to isolate your devices, especially if you're testing some kind of wireless protocols, or you just need wireless connectivity, because a lot of people are running laptops in the office these days. All of them have mobile phones, everything else in between. We were looking at a couple of hundreds devices in the office connected at every second, which creates a lot of interference. So we kind of solved interference with thick walls, mostly isolating the labs into some distant rooms, even renting premises in our city that just used to build a lab in and isolate them there. If you don't have this kind of separate rooms, or you run out of them, there are a couple of options. One of those are Faraday boxes, just mid-sized box, kind of 0.5 meter in each dimension. Radio frequency isolated. They have power pass-through, so they have wall sockets inside the box. They have a network pass-through, so you can connect your wireless router via Ethernet or something like that. The problem with those is they cost like a lot. On average, couple of $1,000 US, maybe even more, but they're really cool. We have several of those, like 3 or 4, I believe. They're occupied 24/7 with different tests, and it's kind of hard to get our hands on one if you really need one in a pinch. Low-cost solution, Google and Amazon RF shielding fabric. This kind of this fine metallic mesh kind of thing. Several layers of those, like 5 and 6, just thrown over your setup will cut off a lot of Wi-Fi interference, a lot of 3G, and sometimes maybe even sub-gigahertz. But the launch box, you're probably wondering why the launch box is here, right? So this is the solution with which we came out in a pinch, where we didn't have Faraday boxes. So we got a launch box, we drill a hole in the lid, route all the cables through that, put a paper towel as a leak indicator, then seal everything with silicone and submerge this into a bucket of salt water. And for 2 days that we needed to run this test, this was kind of a good solution. If you're brave enough or crazy enough, you can run this setup as a part of your CI/CD. I don't see any problem. I don't judge. So it's kind of options that you need to have to think about when it comes to CI/CD for embedded devices, like all bets are off. The last one is purely software strategy. So when we started to pack in a lot of devices in small rooms, they started to interfere in between themselves already. So we isolated them from the outside, but inside is still a mess. So we came up with some kind of a channel separation strategies. Say OTA test can only be run on channel 1 for Wi-Fi and for some other sub-gigahertz. If you develop on LoRa, you probably also have channels. So you run some kinds of tests on one channel, some kinds of tests on another channel, and you do not allow tests to, occupy channels just like as they are free. So different strategies, different tests separated over different wireless channels. All right, so this is part 1, I guess. I will catch my breath a bit. I think we have a couple of minutes if we have questions that needs to be routed directly to me, but I think our guys here that monitor the chat kind of have it good, I think. Yeah. So when it comes to software, sorry, I'll answer all the questions if we have them in the end. When it comes to software, we're using Raspbian and Raspberry because, well, it's an obvious thing to do. It's supported, guaranteed to be run on Raspberry. They have different kernel tweaks specifically for the board. A lot of software is compatible with Raspbian. A lot of software is in their package management. So it was kind of obvious choice for us. When it comes to flashing the image onto the SD card, use whatever you have at hand. It's not a problem. You don't need to have some kind of assembly line, that pumps out the SD card. So we use shell scripts with DD, starting simple again. We use GUI apps like Etcher, like Raspberry Pi Imager, whatever you find fancy. And then we provision this Raspberry Pi. Again, we started with shell scripts that are SCP'd onto the Raspberry around there manually. And we kind of keep rolling with that approach too. It's enough for us. On a couple of projects that I've switched to after, joining the company, we used Ansible, but kind of just to learn Ansible, I guess. This is not a requirement, but if you know Ansible or Chaff or anything like that, you can use that to provision your Raspberry. But this is just for, I think this is just brownie points. So one of our oldest projects even switched to repacking all the software inside the image and just they kind of flash the already prepared image onto the SD card. But again, that's not a requirement. Start small, start simple. This is the mantra you should follow when starting. A lot like couple of tweaks. We ran a lot of default settings in cron tab to be applied after the reboot, because sometimes it's simpler to just reboot the whole stand instead to somehow reason why it is hanging or what to do next. So all the different states for default states for GPIO, this will be dictated on how you say connect your relay in what configuration, and everything else like IP tables, DHCP settings, anything else that you can think about, put that into the cron tab too. For the software that we install on every Raspberry, because they're kind of generalized, even when some of them are specialized, different runtimes. We use Python for tests. We use Java for agents for our CI/CD systems and for some tools. We use Golang for some tools. A lot of tools actually are available in Golang. I think it's cool. Then Git to pull our code from all kinds of dependencies that some of the packages that are available in something like pip for Python or other library registries, some kind of OS dependencies that aren't installed for those packages. This is usually a case for JTAG, where there's a lot of vendor software that need to be installed. For BLE, a lot of libraries need to be installed, and everything else specialized that you might run, for your power monitors, etc. And then wiring Pi, this is just the utility to control the whole header, the pin header on the Raspberry Pi. We use that instead of running with a programming language library, say like RPI.GPIO, because we sometimes log into the Raspberries and do things from command line. Wiring Pi is really good as a command line utility, and you can just wrap it into some kind of subprocess call if you need to use it in your programming languages. So our main weapon of choice for testing is Python 3, because a lot of batteries are available in Python, especially when it comes to hardware and communicating with hardware, and because we know it, basically. So for UI communication, PySerial is just a godsend library. A lot of our folks are actually using PySerial instead of a command line utilities like Minicom or TTYlog or anything like that, because it's just that good. It has an extension that allows you to plug it into your asynchronous code. We ran a lot of projects with asynchronous approach in Python and a lot of projects with blocking approach. We kind of switched to blocking in the end because not a lot of hardware libraries support asynchronous Python. But if you kind of want to experiment with that, PySerial has async IO support. I cannot say something like that about BLE because all 30 libraries in Python for BLE, they're just horrible. I personally use get Python, and I even written an asynchronous wrapper for it because I needed those. And when I expected the code, I didn't understand why it worked. But for some reason it worked. And that is the case with a lot of libraries when it comes to BLE or BLE in general. BLE just shouldn't work, but for some reason it works. Some of our folks use PyBlue. I cannot personally vouch for that, but I think if they used it, they found it okay. And you kind of need to experiment with this space and see what works for you. For the JTAG, we're using the JTAG programmers that is compatible with Segar software, and PyLink Square is the library that is compatible with those Segar software. The pip has just a PyLink package, but this is not related to JTAG at all. So be careful if you kind of use those two. For ADCs, we kind of found ADCs compatible with Adafruit libraries. I think it is compatible with a lot of ADCs out there. And again, everything else that's specific, power monitors, I think like DP5005 has a Python library. You need to kind of experiment, see what the market has, whether it has, the libraries that you can plug into your programming language of choice. On the pure software side, we use PyTest. It's a very powerful testing framework, kind of hard to grok at the beginning, especially when you come from your classic, JUnit, XUnit approach, because they do a lot of things differently. There's a lot of magic under the hood. A lot of things are implicit. But in the end, PyTest is partly what influenced the design of our final pipelines. So I guess I'll have a couple of slides, just a quick crash course into PyTest as well. Like I said, we used for a lot of devices, even those powered by Linux that has SSH service capabilities, kind of running onto them. We use serial port, but if you need SSH, SSH is available by two very, very good libraries. So Paramica is, again, a synchronous approach. Async SSH is asynchronous approach. Or if you need to offload anything to a cloud instance from the Raspberry or for a local powerful desktop, we kind of use SSH for that. HTTP can like download all this stuff, upload all this stuff, create mock servers, kind of mock your backends, and do everything in between. Request kind of famous. I don't really like requests though, and not even because of the drama that happened with it. That HTTP, the only right way to do HTTP is an asynchronous way because it's an IO bound operation. We have libraries for those. HTTP is really good. If you don't want to learn a new API, HTTPX kind of copies the requests API and does that in a synchronous way. The last couple of libraries are just for retrying. I don't endorse this type of coding, like just slapping a retry decorator on top of the code that misbehaves, but sometimes it's not because you can't find out the root cause, but some outside factor, solar interference or something. So on a mission critical code, we have this retrying decorators carefully sprinkled on. Just sometimes it's easier to try another time to fail the whole test. So like I said, a quick crash course in PyTest. They have this concept of fixtures which replace setup and tear down code. Those fixtures can be scoped, so their default scope is a function, so they are ran once per test. Then you have module once per file, session once per whole testing session. So we use session fixtures, for example, to create a simple device object, minimally populated, minimum connections, or you can put something there that is really, really expensive to create and run it only once and then share it between every test you run. You can also figure out dynamic scoping during runtime via command line arguments, something like that. Fixtures in conf.py are available globally. You don't need to import them. And they're just really neat named pieces of code. When you build an infrastructure, or rather not an infrastructure, a hierarchy of those fixtures, you can reason, create a simple serial device on a scope session, then later specific device with, say, power measurement capabilities and several SSH connections into that specialized fixture. And the other thing is mark. The mark's simplest purpose is just to group tasks into sets, and that will later allow us to run just customized pipelines with a couple of command line arguments. So arbitrary names for marking is allowed. This test is marked just Wi-Fi. Wi-Fi is not a built PyTest feature, it's just the name we chose for it. And then for built-in fixtures, for built-in marks, rather, use fixtures is just a fixture that you can apply on top of the test without passing it as an argument to the test. Sometimes useful for fixtures that doesn't return anything but should be applied to every test. Skip if, simple conditional skipping. And parameterize is a test case multiplication. Basically, so you can run one test, one test, parameterize it with a lot of parameters, and that creates multiple test cases. And that kind of differs from something like using for loops inside tests and looping through all these parameters, because in for loop, when you fail one iteration, you fail the whole test. And even if you don't do that, the multiplication by parameterize allows you to kind of apply the fixtures, for example, with their corresponding scope. So if you have a function fixture that needs to be run every test, parameterize does that for you automatically. And then you can use different marks inside the marks and go really, really deep into the rabbit hole. But in the end, PyTest allows us to just write really simple tests and then blow that off into thousands and thousands of different tests, like specialized for some hardware or something like that. And I don't want to kind of, when it comes to how to write your testing code. So PyTest is also an option. You can use whatever you want. But the most important part, in my opinion, when you're trying to test embedded devices is just the code that operates with your logs. Because while you have a hardware that tests, that helps you test your devices, like light sensors, power meters, oscilloscopes, anything like that, in the end, your main source of truth, your main source of test relevant information are logs, especially for multi-step tests when you need to wait for some event to happen before proceeding. So log monitoring code is important. And in my opinion, log monitoring should both support real-time log parsing. So say you do provisioning and you need to wait, and the logs are in real time streamed. In case of, real-time OS devices, they're usually just streamed inside the console of the processor. When you run Linux or QNX device, you may have something like journal CDL, some kernel logs in dmask, or just a log file that is stored somewhere on the device. And you need the ability to parse those logs in real time. And on the other hand, when you run a long-running test, especially when you collect some kind of statistics, some kind of KPI, and you need a lot of data, and you cannot do those calculations just in real time, you need to collect, in some cases, a couple of gigabytes of logs, for example. So log monitoring code also should be able to stream those logs on top of Raspberry or any other storage you use and store them somewhere for subsequent analysis. One problem that we ran into trying to extend our logging on real-time OS devices is that when you start to improve your device, add new functionality to it, it kind of eats into the RAM, and some devices have really low RAM on them or a low flash amount of flash storage. And the first thing you kind of want as a developer to cut to fit your new functionality is just the login verbosity. The problem is when your tests rely on those login verbosities, and we're talking something like trace levels sometimes or a lot of times, you kind of need to figure out a trick of how to save those logs so you just don't throw away your tests, because sometimes it's just impossible to create a test without a trace level logging. So we came up with something we call stenographic logs or binary logs. It's just assigning short codes like exit codes and something like that. So the log line might look like 1411 semicolon PBZ 38, and then it's human unreadable. But during the build process, when the firmware is built, we generate the deobfuscation map with a simple JSON file that parses those short messages into the long sentences. And that approach allows you not only to, not touch your tests. If you've written those for human readable logs, you just add this simple transition code inside your log monitor so you can transition in real time and even store those logs deobfuscated. And that's it. And you can dynamically turn it on and off depending on the device. So some of our devices use stenographic logs, some of our devices use usual human readable logs, and we run the same code for both. So we share a lot of code. So then it comes with all these capabilities, we're going to start to design our CI/CD pipeline, something like with a microservice approach instead of the monolith we had in the beginning. Of course, the truth is somewhere in the middle. So this is kind of a hybrid approach, but we save our original build pipeline. So the one that you had even before we started, just check out build, maybe run some unit tests. And we then store that firmware in the storage if the build passes. Passes are simple testing like basic acceptance tests or unit tests. And our test pipelines, instead of breaking the build itself, they influence the status of the firmware in that cold storage or in that publishing service. And that allows you to kind of develop on different paces. So you not block, for example, built-in pipeline with your week-long tests. And you can multiply the number of the pipelines you run over that firmware just simply by passing some kind of a PyTest -m, which is short for mark, selecting that this pipeline should run tests for Wi-Fi, and this pipeline should run tests for OTA, and this one should run a test for security. You can even store your security test as a part of your just general testing code. And those pipelines can be hard-coded especially if you run them like on the cooldown, one finished, the other just started. You can run them by the build trigger. You can run them as nightly pipelines. Whatever strategy you come up with, I think is going to be good. And the same thing we can use for our SAST. And like I said, your DAST pipeline can be just part of your usual pipeline. Same thing we can use for SAST. To be honest, just run a SAST as a different pipeline and inject it somehow between our checkout and build or in parallel with build. So we use this approach, scanner as a service, where we go to the developers and say, listen, all you need to get SAST into your pipeline is this 5 lines of code, nothing to configure, one-time operation, you put it there, and everything else is handled by us, the security. Because developers, like in my experience, they're really lazy when it comes to security. So you kind of need to game the system a bit, give them some kind of incentive. Maybe you want to give them additional privileges, faster releases or something like that. And then they set it and forget it, and you do everything in your pipeline and you control everything. So for SAST, we run for each language we use. And we use a lot of them because we also scale this approach often embedded to the backend, to a mobile app. When you control the pipeline, you can kind of play with any kind of security scanner, and the developers won't even know. So we run a language-specific scanner as a part of our pipeline, a dependency checker, and then some kind of a secrets check that checks for hard-coded keys, some kind of tokens, certificates, everything like that. And this pipeline is just a string of Docker containers that drag the code through each scanner. We collect those results. We don't immediately react on those results. We collect those results into one big report and then run custom logic on that report and decide whether we should output basically 0 or 1 up to the developer pipeline to say whether they passed our checks or not. And custom logic allows us to do things like integrating it with vulnerability management platform to check for false positive results or check for some kind of other things. Unfortunately, vulnerability management platforms, they're not silver bullets, and more often than not, they just don't work. So we can run some custom vulnerability management database that we establish ourselves and do the same kind of thing. And in custom logic, you can also say, just enable the critical vulnerabilities without even changing the flags for the scanner. So let the scanner scan everything, and then we just react on critical vulnerabilities. This is especially useful when you're just starting to introduce SAST into your project, and your developers wrote your code for whoever knows how many years before and never concerning with security. That thing is going to be written with critical vulnerabilities. And they will be coming to you and saying everything is breaking, what have you done? So we react on only critical, eradicate that, and then we enable high in our custom logic and react on that. So you can kind of gradually increase the number of security checks, and it's going to be transparent for developers. They don't need to do anything. You don't interact with their pipelines in any other way. Also, you can do per project tuning capabilities with this kind of pipeline. Say the project with the name X comes to you, so calls your pipeline. And then you know that for this project, you need to run an additional scanner, or you need to disable some checks, or you need to install some dependencies first because it cannot be scanned with a specific scanner That almost always happens with scanners written in Java for some reason. I don't know. Yeah, so you can kind of do this tuning and control everything yourself when you run SAST just as a pipeline itself. With this approach, though, the only caveat you need to think about is that you don't want to break everything for all the developers when you make changes. So you kind of need a pipeline to test your SAST pipeline. And we are now at level 3 of embedded pipelines. This doesn't go any deeper, but if you can think whether you should do one level deeper, like props to you, go there, experiment with that, have fun, I don't know. And the same thing with DAST. Like I said, it's just a part of the testing code, same code base as other tests. You also run DAST as just your pipeline. You can run DAST in your build pipelines, but sometimes it takes a long time, and you don't want to block the developers because then they come to you with the pitchforks and start nagging you. For DAST, we kind of ran some commercial scanners, especially when it comes to IoT embedded devices, but the most simple thing is always the most useful, especially in this, when you just begin to do this thing. You want to cover a lot of ground. For covering a lot of ground, just port scanning with Nmap or anything like that is just enough to start rolling out your DAST pipelines. And also, especially if you disable your UART and JTAG consoles in the software, but even if you don't, if you blow your eFuses physically, you also want to test that those things, especially in production firmware, are disabled, because it's just the easiest thing to get into your device and start, poking it from the hacker kind of perspective. And then when you build this kind of foundation, very simple foundation, you can start to specialize with DAST, do some wireless testing. So again, good luck. Wireless testing software is horrible. But this is kind of the most simple test you can do too. You can try to dump flash from your device, see if it's encrypted, or confirm rather that it's encrypted, and everything else. You can even try to do some kind of glitching, and break your secure boot as a part of your pipeline. Good luck with that. But Chip Whisperer can be connected to Raspberry via USB. And everything else that your internal and external pen test finds, you can kind of think about it and try to automate it and convert it into your DAST. I think sometimes people forget about that too. Just pen test is a pen test, and like CI/CD and testing automation is just testing automation. No, you can just borrow some things from the pen test and then maybe share some things with your pen testers if you have an internal pen tester team as a part of the test automation team. Like say, hey, we have this cool flashing tool that will save you 20 minutes on your next pen test. And you kind of build this kind of cooperation between your departments. All right, demo time. Wow, things like time passes. Who would have thought? So live demos. As always, what could possibly go wrong? Wouldn't it be fun if Cloudflare just kind of goes out right now and nothing works? So when it comes to, let me show you the setup actually. So we are starting simple. We have this kind of thing, the Raspberry Pi that is connected to the ESP32 board, because we're just cheap, and we run the free tier of GitLab. But with things like this on a budget, even especially when you're a hobbyist, I don't know if we have any hobbyists connected right now, but if you're a hobbyist, $5, ESP32 board and $30 for Raspberry and some change for USB cards, you can start doing this thing without breaking everything in your organization, and then take that experience and kind of build on top of that. So Raspberry Pi, me personally, in my company, we still use them. We just have like something like 200 of those already deployed over different locations. Guys from TechMaker were cool to provide their own solution. So the thing on the, yellow carpet thing is the custom board designed to emulate the system from the whole car, basically. Yeah, this one. And then they connect different things to it, and they can push, they develop CAN bus scanners, right? So they can push any information from this board into their CAN bus scanner, and then connect something even like Raspberry Pi to it, and just use these techniques that I talked about, and a bit of, craziness and imagination to design their custom test for their custom hardware. So and when it comes to the code itself, this is just a simple espressive ESP32 project that you can run on your device. So what we have there is some kind of code. I'm not an embedded developer. I tried and failed horribly. That's why I'm embedded pen tester right now. So we have some kind of code, okay? And then we have some kind of test. So we use Unity as a C testing framework. Am I correct? Yes. So we use Unity as a C testing framework, and we can run unit tests for, on top of the device itself. So it's kind of cool. If you want to do that, you can do that. We output some banners to just simulate whatever logging you can do, I guess. And then we have this thing that just runs the test, the readout test. What we do is just open a serial connection and start reading logging. This is definitely not a super robust log monitoring code, but I kind of pour a lot of effort into that, and to show it during a demo and explain every decision is simply impossible. So we read our logs, find a report start, and when we find a report start, we'll kind of act on it. So, I should have probably launched the pipeline so it builds. Let me quickly do that, and then we kind of go and explain things that are happening. Okay, Cloudflare is working. Cool. All right, so when it comes to GitLab, on GitLab, I'm mostly Jenkins, AWS code build, and even our internal software. We have and here, wow, cool. Your internet connection is unstable. Here we have a compiles tab that just builds our firmware, and with this tool, with a tool that Expressive provides, it builds our firmware as a release kind of firmware. And then we have this tab with device under test, which is our ESP32 board connected to the Raspberry, that does everything like that, plus flashing it under the firmware, and then running, flashing it on the hardware, and then running the unit tests on the hardware. And then we have SAST, kind of SAST. So when it comes to GitLab, enabling SAST on your pipeline is just as simple as including their template. They have some predefined scanners there that run into, again, in a Docker containers, just like we do, but we do that in our custom system. And this template automatically detects the kind of language you're running into your repo. If it's a multiple language, have the same script for secret detection. So how it looks and how we build our pipeline is that the test tab, I don't know if you guys see, this is it. This is the CI/CD pipeline on a GitLab. But what it does, it actually runs a lot of scans. So it detected a Python code in our repository and runs a bandit scan, which is a SAST tool for Python. It detected C code, obviously, because it's a firmware code, and it runs a flow finder. And then we have a secret detection. And then here we have things building on the Raspberry Pi itself, while this runs on some cloud instance. Let me show you real quick. Settings and CI/CD. They have this kind of runners, and they give you some shared runners for free. So this is just a cloud instance. You go there, you enable it here, and you have the ability to run SAST on your pipeline real easy. And then we have a custom runner setup with our tags, RPI and shell. So this is a GitLab runner running on the RPI. So you can mix together even x86, and ARM in the same pipeline. What kind of interesting thing we figured out when we're designing this pipeline is you can see that everything from SAST passes here. Every secret detection is passed. What you don't know, but by the way, we'll share this repository after the presentation. So ping us if you need a link to it, or we just put it into the channel and publish it. So yeah, back to the SAST. Well, secret detection looks like it's okay. What it doesn't see is that we have an AWS credentials committed into the repository. And that is the thing with GitLab, at least free version. So instead of breaking the build, it just generates the report for you to inspect. So if you go there and click on the artifacts, you gotta see that there are a lot of artifacts already generated. And when we go into the secret detection artifact and load it and open it, we can see the report. This is the Git leaks tool, which is a tool to find all kinds of tokens and certificates and private keys. It kind of generated the report for us, so it had a finding, but it didn't break our build. And that will be probably, in this case, the job for your custom logic. But when you start running custom logic, I guess you kind of forego this idea of doing just a simple template detection and you're doing everything custom. Now, this is what I don't like about GitLab in this kind of thing. And also, you don't have, with just a simple template include, you don't have the ability to customize your scanner. So let me show you real quick. I run the scanner that we do, which is Detect Secrets. Open source scanner created by Yelp, not perfect, but if I run the scan over the same code, it finds some other findings. So there is a secret keyword in our credentials. That's okay. There's the same credential file. But we can see that there's something in app.c that it considers a valid secret, or rather the secret you shouldn't have been committed to the repository. And what that secret is actually is just a hard-coded Wi-Fi password in our firmware. So Git leaks doesn't find those because it's not designed to find that thing. It's just designed, I guess GitLab is kind of a, web first company. So they're designed to find your cloud tokens, your API keys and stuff like that. So we have this hard-coded Wi-Fi password in our firmware that SAST scanner just simply missed. So you need to pay attention to those. You need to evaluate different tools. You need to even evaluate tools from the perspective of threat modeling, whether you want to use them or not. I know in big companies, there are even departments that do that. And, even legal department can prohibit you from using the certain tool, or maybe if it's it's a PVS Studio, you kind of just need to do threat modeling because of where it comes from. But some vendors, and we've caught one of those too, they just siphon a lot of unneeded data, unneeded for them, but like personalized data from your code. So we had a talk with one of the vendors earlier, and I guess we stopped using them too. All right, so what happened to the build process path? Yeah, and then for the Bandit, it also, so this is how it looks inside the container, by the way, just running analyzer and outputting the results. For Bandit, for example, just so we hear, there are some findings in this report, as you can see. But those findings are, again, irrelevant. It's just use of a sort detected. Some scanners are really panic a lot over some simple code. So there are options to disable these checks altogether, but that's, again, where the custom logic kind of introduces itself. Do you want to do that for every pipeline forever until it change you, until you change it, it changed you. Wow. Yeah, until you change it, or you want to do some kind of per project customization. What else? It's kind of interesting. I had this thought about SAST. Yeah.
False positives.
False positives will be bane of your existence, guys. Like, no amount of vulnerability management from different vendors will kind of save you from this random false positive that you have. Yeah, I remember what I wanted to say. It's kind of funny story. So, like I said, developers are a lazy bunch. Like, no offense, guys, if you're a developer, but from my perspective, like, really lazy, especially when it comes to security people. Like, they say, don't touch us, like, let us do our coding thing. Sometimes they get really smart and just put those kind of comments and pragmas in their code that tell the SAST counters, just don't treat this as a vulnerability. And if you don't monitor for that, especially if your tools don't have the ability to ignore every kind of ignore, it's kind of on what amount of levels are we here? So yeah, ignore every skips in our test scan. Some tools don't have that. And unfortunately, if your developers are really, really tricky, they can kind of just outsmart your SAST to the point of just disabling the checks altogether in their pipeline. So you may want to run code that checks that kind of thing, just disabling your checks altogether. Just pull their repos from time to time and just do a grep to see if your code is commented. And for tools that don't have the ability to ignore all skips, again, just, pull the code, run a sed, remove everything that is ignoring your code, and then run your SAST scan. But that is just when your developers are tricky. That's sometimes that happens. So you need to consider this kind of possibility too. All right. Do we have a successful build, by the way? Oh yeah, we have. So here's what this thing we built on the Raspberry Pi. I guess it doesn't show that we built it on a Raspberry Pi. Yeah, also it's an Arch ARM OS Linux. And then those kind of tests that we ran from Unity, we ran them from this converter, Unity to JUnit. So we just converted the Unity test to a JUnit or XUnit format that a lot of CI/CD systems understand, because that's actually a very ancient format at this point. But they all support it. We ran also a plugin for PyTest that converts those to HTTP reports. They're really useful when you're reviewing, thousands of tests and 34 of those are failing, and everything else you need to just filter out. They have these templates that you can quickly filter out, but GitLab does this for us, again, converting JUnit or XUnit to HTML reports. We have two tests, and both of them are passing. The tests themselves, let's just quickly search this. Max function. Yeah, the test case themselves just also really simple. And just like that, we have a simple CI/CD pipeline built in. How much time did we spend on this? Like really, really small amount of time.
That's 2 or 3 minutes.
Yeah, two or 3 minutes. Yeah.
But you can actually use shared runners for to build your firmware and then push it.
Yeah. So the design decision. The design decision of this pipeline was basically we ran SAST and test our code before building our release firmware, but you just mix and match those steps however you want. Yeah, we built this pipeline really quick because everything else that I talked about today is kind of a experience from previous 3 years at least, combined just, simple presentation. I guess that's everything we wanted to say right now, but if you have any question that you might want to ask, some specifics, maybe to continue with developing this kind of pipeline together, then probably shoot us a question in Discord and we will be happy to answer you. do we have any questions, by the way, that are left unanswered by you? No.
Yeah, actually, we can talk about.
Oh yeah, Andrew can talk about their own device.
We have like 45 minutes.
Yeah, we have 45 minutes, and he wanted to talk about this custom board that he built. So you want to take the mic from me? Or you can just scream in my face and people will hear. Okay, I'll come closer.
I think you should.
Yeah, I should open OBS Studio. So okay.
So yeah, basically what we have done is this device is actually I'd say it's like a middle where between your laptop and your actual device. Right here you can see a car alarm system that is connected to this I'd say car emulator or something like that, because right here we can emulate actually any activity that is presented on some vehicle, and through the USB we can push updates to this middleware and, for instance, use our CAN frame that we have collected from the real vehicle to emulate it and to see if this device performs well under these conditions. And by the way, we can sure use another USB cable, just connect this device and update its firmware as well. And this way you can actually push any data, especially from some exotic buses like CAN bus. It may be even some radio frequency channels that you can use for connecting to this device or something else, and then push all of the data to your laptop, where you can prepare those reports like we mentioned before for your pipeline, and use it in your SAST and DAST pipelines to check all of that, and as well as your firmware itself.
Right. So this is just on a whole different level. So the guys went and designed their own board from scratch. I guess they talked about that in their presentation yesterday, just designing things from scratch. Did you? Yeah. Okay. But when you want to run on a budget, and especially when you want to run a lot of devices on the Raspberry Pi itself, when you want to run many devices, you can probably use Raspberry Pi because it's just a cheaper solution than going out and designing everything and printing it and running it as a part of your lab. In our company, we run, I guess, 15 different device families. When it comes to Raspberry Pi, they really handle them all well. We run one per device just because we run such a vast array of different devices, kind of like different, but the same, but still different. So we don't want to write a code that will differentiate between the devices on the Raspberry itself, because that runs into a lot of problems, especially with knockoff adapters. They kind of have similar or the same serial interface, serial number, so you cannot differentiate between them only by the serial number. And then the USB enumeration mechanism, when you connect those things to the Raspberry, doesn't guarantee that you will receive the same adapters as the same dev TTY devices. So there is no guarantee this device connected to the Raspberry will always be TTY USB 0 or TTY S0. So that's kind of why we selected to go with a single Raspberry per device rather than connecting a lot of even homogeneous devices to the Raspberry. If it's okay with you, then I guess good for you. Go for that. Try that. You can even try other boards. We evaluated Asus Tinkerboard and Odroid H2s at some point, but for us, it was simply a matter of availability. We can buy Raspberries by like tens and even half a hundred of them in one batch, while those other boards that are not as available. They don't have the same kind of extensions we might need in the future. They don't have as good of a software support. But yeah, in the end, it's all up to experimentation. I just gave you guys some ideas and some kind of pitfalls you might run into when you start doing this thing this way. Maybe you can figure out to run anything even cheaper and even easier. Probably give a presentation. I will come and listen to you too. So thank you. I think that's everything I wanted to say today. My email is on the slide. We have a Discord channel that's named TechMaker-Lab. I am THA there. If you just want to drop into the private messages and discuss something in private, you can do that, or use the channel itself to just kind of ask some generic questions that you might think the answers to which you might think might be useful to everybody else, so you just don't keep it to themselves.
We have some time. I think we can show how actual reports from the Raspberry through the screen or mini home.
Yeah, probably, yeah. So you just guys, so you don't think we're faking all this stuff? Here I have a Pi at HITB, totally legit Raspberry Pi that's standing there, and like this is no joke. So we have PKHOM -B. I'm old school. I don't use Pi Serial for that. They have TTY USB 0. All right, so when we press Y, we run into some kind of watchdogs for some reason, but this is running on our GitLab connected Raspberry, and this is the device. And
press Y again.
Yeah, and I'll press Y again, and to test running. Sometimes this thing, we put that into an endless loop at some point.
Actually, yes, because we have the only tasks, so that's why we are just waiting for the Y.
The Y. So this is a real device, not an emulator. By the way, if you can use emulators in your pipeline, that's kind of an interesting choice too. But we tried to do that, and we ran into some problems of just designing emulators for different SoCs, because some people, some companies, just one product company, they have one SoC or one microprocessor, they can do emulation there. We unfortunately had to do this the hard way and just design all this kind of crazy thing. For some reason it works. I don't know why. Frankly, I don't know why it shouldn't work, but it works.
And yeah, for the real embedded devices, you actually have no emulators at all, because you have plenty of other peripherals that you should emulate.
So this is the problem with peripherals too, for sure, because I think it was 2019, somebody from Google shared some fuzzing for embedded devices, but yeah, that's kind of a simple situation where you have to care only about SoC that you're emulating, but with the real hardware, it's just a lot of peripherals for sure, like buses, I2C, CAN, JTAG.
These actually are cutting edge technologies right now. SDR, Chip Whisperer, these tools are actually made for fuzzing different peripherals. But not emulating them.
Yeah.
So maybe we can show
our Chip Whisperer that I have at my home. Yeah, nice. neatly stashed somewhere deep inside the closet. Right. But yeah.
SDR boards.
SDR. Yeah, you have an SDR board. So let's just run with that. Somewhere stashed deep inside the closet. Yeah, we use a lot of hardware, guys. You won't believe how many hardware they have there. So they just stash the most useful ones as far.
A simple one.
Yeah. So do we use OBS for this? By the way, I don't trust my camera at all. So this is an RDL SDR, $30 I think. They just repurpose it. $15. They just repurpose it from some TV tuner, and it allows you to, FM radio, I guess, right?
FM radio, yeah, up until 1 gigahertz. Maybe.
Yeah, so sub-gigahertz is possible for this thing. If you're running some kind of LoRa or maybe, what else, Zigbee or Z-Wave, well, what is lower frequency of that? I think they have...
I think it was sub-gigahertz.
They have something around in 2 gigahertz range too, I guess.
Our fun box.
Yeah, so this is the fun box.
Oh.
Yeah, I have OBS running, no problem.
Sure. So here it is. So actually, when we try to collect some data from RF signals, we use this board. This is actually Blade RF.
Blade RF 2.0, A4 micro something.
Yes. It has 2x2 multi-input, multi-output connectivity. And of course, you should use different antennas for different RF signals. So that's why I have plenty of them right here. And of course, we use for some
simple
setups.
For simple testing, RTL SDR is okay.
Is okay.
Different antennas, some of them are 433 megahertz, some of them support 4G, some of them are really custom made for nefarious stuff, I guess. Right, directional antennas, omnidirectional antennas. So again, just limited by how deep are your pockets.
Actually, these two might cost more than this board.
Yeah. So when it comes to prices, SDR is one of the most expensive things you can use probably when you're testing embedded devices. Short from something like, if you use lasers, you're probably not coming to this talk. You probably know more than me if you use lasers for testing embedded devices.
But it gives you almost endless possibilities.
Yeah.
I think you clearly understand why the thing is here.
Right. So we can test some kind of other embedded devices like, smart cards.
And smartphones.
And smartphones. Yeah. So this approach, by the way, like the Raspberry approach, is good for designing off-the-shelf devices. So when it comes to developing embedded device, you usually have different stages. So engineering validation stage, that usually comes as a first batch of boards, really unstable. And for us as a test automation team, when I was the part of the test automation team, we almost never saw EVT devices because they were all occupied by our developers. When it comes to design validation testing or DVT, that is the next stage, we can kind of start seeing some kinds of devices. We can borrow them from the developers. We can start connecting them to our stands. Those stands accept pretty much everything that a company produces, doesn't matter if it's new or old. But you probably will have the most availability will be for already released devices, so mass production devices. You just go to the supermarket, basically, and then just grab a lot of those from the shelf. If you are, a pen tester that does bug hunting for embedded devices for a living, you do basically something like that too. You go to the Best Buy or whatever local supermarket, Walmart you have, right? You just grab everything from the shelves, baby monitors, webcams, all the different stuff, and you start poking into those. So this kind of setups, you can automate some fuzzing, for example, with it. And we use that in your future projects when you go to Best Buy again. But for off-the-shelf devices, I think like Raspberry approach is much more suitable than designing some atrocity like this kind of module, the black one. Can you just view the antenna? All right. Everything else? Anything else? Yeah, he has nothing. I mean, terrible. All right. So I guess that's really, really all. We kind of. I just kind of, shot it in like a machine gun for some reason. But I hope you understood everything. If not, just come to the chat and we'll see you guys on Discord. Thank you for coming. Have a nice day. Stay safe and see you later.